Thank you so much for that nice introduction. The amazing Kim. Wow, she is just unbeatable, right? Hey, look, it's my slides. Thank you so much for coming, you guys. I know it's after lunch. Try to stay awake. I'll try not to be too dull. I'm talking about NASA, and it's my favorite topic. And anytime you're talking about NASA, you kind of need to have some disclaimers involved. So there are a lot of projects at NASA. There's like 50,000 people when you count all the employees and all the different contractors. And there are 10 NASA centers at which I only work at one, so I don't really know everything. But I'm going to talk about what I do know. And if you know something I don't know, I want to know it, so please come talk to me after. So about those 10 NASA centers, this is my completely unbiased map of where they are in the U.S. Completely unbiased. I work at Jet Propulsion Laboratory, which is in Pasadena, California. We're a little bit different than all the other NASA centers in that the other 9 are owned by the U.S. government. We are owned by a college. So the story goes that like 80 years ago, there were some college students who were super into rockets, and they just kept blowing stuff up in their backyards in Pasadena, California. So the neighbors objected, unsurprisingly, and Caltech, the college they were going to, said, you know what, we're going to buy you some land that's away from all the houses, and why don't you blow stuff up there? So they did. And then a few years later, Jet Propulsion Laboratory was born on Halloween. Best birthday ever. So that's preceding NASA. When NASA come along, they were like, oh, we actually need to get spacecraft out of the atmosphere. And you know what helps is jet propulsion. We should buy the Jet Propulsion Lab. And our founders said, no. How about we'll be a NASA center, but we're going to continue to be owned by the college because we don't really want to be government. We'd like to be the black sheep. And so we still are. In the 80 years that we've been a NASA center, we've launched 100 missions. You may have heard of Voyager. Voyagers 1 and 2 launched in 1977, and it's 40 years later, 41 now, and they're still going. We just recently fired Voyager's thrusters for the third time in like a year, and she responded. She is out past the edge of the solar system. She is the furthest man-made object from Earth, Voyager. We also made Curiosity. You may have seen when she landed, they call it the 7 minutes of terror because it takes 7 minutes for the data to get. So if she had crashed on Mars when she landed, and by the way, we don't say crash, we say rough landing. If she had had a rough landing, we wouldn't have known for 7 minutes. So there was nothing we could do, so we were kind of chewing our nails in the control room. She did fine. She's outlived her prime mission, like everything else we do, and she's still going, sending back pictures from Mars every single day. We also did some other Mars rovers you might have heard of, Pathfinder, Spirit, and Opportunity. Spirit and Opportunity are one of my favorite stories because they were supposed to last for 3 months, and Spirit went for 7 years, and Opportunity is still going 13 years later. So JPL missions are super over-engineered. These things are built to last. And it's because failure is not an option. You guys have all heard this phrase from the moon landings and stuff like that. But what it is a two-sided sword. Failure's not an option, right? Rah, 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 we can do this. We're going to make it happen. We're scrappy. We can do this impossible thing. Failure's not an option. But the other side of that sword is failure's not an option. If you screw up, you only get the one screw up because a screw up with a NASA mission is like $1 billion of taxpayer money wasted. You never get another chance again. So we cannot fail. And for that reason, everything that all of the NASA centers do is tried and true, very rigorous processes of testing and engineering and carefully modeling every activity. I mean, you have no idea the rigor these guys go through to ensure that we're not wasting taxpayer money, we're not blowing things up, we're not losing science, we're not losing people. NASA has a discipline called human factors. In most of the NASA centers, the human factors people are there to support human spaceflight. So the space shuttle people, what's it like to do stuff in 0G? It's actually incredibly hard. How does your cognition change in 0G? Super, super weird. It's also all about aeronautics. What's it like to be in a cockpit? How do you maintain situation awareness when you're flying a piece of equipment no one has ever flown before? What it didn't cover until pretty recently was software for the ground personnel. So every mission has those people in mission control, right? It's also got people behind the scenes who are gathering the telemetry from the spacecraft. They're getting those pictures and turning them into something that the public can use. And they are looking at the spacecraft and what it's doing, and they're tweaking the commands to the spacecraft to tell it what to do next. And NASA had built software for those people, and it was good software. It was rigorous, it was well designed, it was super well engineered. But was it easy to use? No. So along comes the Human-Centered Design Group. And this is a group at JPL that was formed about 6 years ago. We're tiny, there's 12 of us. And we said, hey, NASA, you know that 80-year-old process that's totally tried and true and has been 100% successful for you because you're awesome? We want you to change it. No big. And of course, NASA was like, what? There was this immune system reaction, right? No, we're not going to change things. We're doing a great job. Why would we change? And we were able to show them that, look, you are doing a great job, but you can do a better job. You can have smaller operations budgets. You can use more of that money for the mission and the science and less of it to figure out what the spacecraft should be doing next. So let's talk for a minute about how NASA missions, excuse me, I'm going to grab some water, how NASA missions become missions. If you Google NASA mission phases, you'll find this thing with phases A through E, and it's kind of complex and it's a little bit fuzzy in some places. This is what you really need to know. Everybody loves chevron diagrams, so let's explore one. Concept is your first part. This is where somebody gets an idea for a mission that can solve a problem or answer a science question. Next, from there, it goes into formulation. This is where you work out all the details of how this spacecraft comes together and where it's going to go and what it's going to do and how it's going to do that. And then there's implementation. You got to build it. You got to build the software. You got to put the processes in place. You got to figure out when you're launching. You got to get a launch vehicle. And then operations. Once you're off the ground, then there's 2 to 7 years maybe of travel. And then you got to do a bunch of science. You got to tell the spacecraft what to do. You have to help it react to stuff. You have to give the science data to the scientists out in the world who will make amazing discoveries with it, like dark matter or extrasolar planets or all of these amazing things, and maybe someday life, right? Life outside the Earth. That's the big goal. So for us, our foot in the door was at the end of that process. It made sense for us to say, hey, in the operations phase, you have software. Guess what we do? We do software. So let us come in and help your operations software be easier. This is all software that we use on the Deep Space Network. It's pure operations. It's how we talk to all of our spacecraft that are further away than the moon. So we proved ourselves by designing software that made operations easier, that made it much faster to find problems, troubleshoot them, and fix them, and that made the operators able to understand what was going on all over the network. We also did operations software for Curiosity and for a few smaller missions. And as we started proving that we could do this and that it actually had an effect, we saw that the NASA engineers started to really open their hearts to us and say, oh, we're empiricists and you're showing us evidence that what you do helps, so we're going to let you help us more. And they let us in at the concept phase. Now, to explain the concept phase to you, there are 2 ways that a NASA mission becomes a mission. The first is that NASA itself, headquarters, it releases what we call an announcement of opportunity. And this is, hey guys, we want to go explore the outer planets of the solar system. You 10 NASA centers, put your heads together, come up with an idea. And then all the 10 NASA centers get together. They kind of come up with their own plan, super secret, don't tell the other NASA centers. And they compete against each other for who's got the best idea. That goes to NASA, and if NASA approves it, it'll move on to the next step. The other way that this can happen is that some super genius principal investigator, we call it, some person with a great idea, makes a sketch, thinks about an idea, says, oh, you know, I've been showering and I had this great inspiration. I think I'll propose a mission that has a new kind of telescope that can see this special kind of infrared light nobody's ever seen. And then they take it, they propose it, and if NASA likes the idea and if it has merit, it moves on to the next step too. Both of these go into formulation from here. And formulation is all about working out all the details, right? You got to know what your science goals are. That's easy if you have an announcement of opportunity because they tell you what the science goals are. But if you're a principal investigator coming up with your own idea, you're going to have to clearly state, okay, this is going to tell us about the origins of the universe. You have to be very, very detailed. Then there's what instruments are you going to use to meet those science goals? On Europa, we have telescopes, we have radar, we have magnetometer, we have spectrometers, we have cameras. And all of those things work together to help us gather the science we need to know to answer the questions, is Europa habitable? Then you need to know your trajectory. Are you going to make a beeline for the planet you're going to study? Or are you going to do this like windy thing and use some gravity assist of planets? You have to give NASA a detailed description of what your trajectory is going to be so that they know where there's opportunistic science, they know where you're saving fuel, they know where you're using too much fuel, and they evaluate your mission on the merits of that. And also, you need to know what your operations plan is going to be. Remember, we're really good at operations, so that's another place we help a ton, is we help them visualize their operations plan super early before even they propose it to NASA, so that they can say, not only can we do this mission for this much money in this time frame, we also think we can operate on this budget. So NASA just knows the next 20 years of that mission before they have ever even approved it or spent a dime. And of course, you have to have a spacecraft, right? It helps to have a spaceship if you're doing space science. And there are like 20 subsystems in a spacecraft. And those 20 subsystems are people. Each and every one of those 20 subsystems has an engineer who is in charge of figuring out. There's usually 3 or 4 engineers, but here we're going to say just one. They're in charge of figuring out what is the propulsion for this spacecraft going to be? What is the power system for this spacecraft going to be? What are the instruments? Each instrument is going to have engineers too. And the old way that NASA used to do this, and the way that a lot of the NASA centers still do it, is one engineer sitting at his desk will enter stuff into a spreadsheet and email it to another engineer sitting at her desk, and she'll enter stuff into a spreadsheet, and she'll email it to another engineer sitting at her desk, right? So this can take months, and as soon as she receives it, he's already tweaking it, so her copy's out of date. The other way that it can happen, and the way that it almost always happens at JPL, is that we get them all in the same room, and they shout numbers across the room to each other, and then they type those numbers into their spreadsheets. The instrument guy will be like, I just added a telescope, it needs this much power, and the power guy will look at his spreadsheet and he'll go, oh man, my battery's not big enough for that, I'm going to have to add a bigger battery, and now I have a surplus, and I have this much surplus, and then the thermal guy goes, oh man, I could use that surplus because we're really cold. But I'm pretty sure you can see the problems in that one too. Typos and misinformation and crossed wires. It's so manual. But this is how we've shipped every one of our spacecraft. This is how we built Voyager, and she's still going 40 years later. So it works, right? We improved it. We were able to give these guys a piece of software that's an integrated modeling environment. So as the instrument guy drags a new telescope in, the 3D model updates. Everybody in the room can see it. The power guy sees that his power graph just went, whoop, oh, I don't have as much power toward the end of the mission as I needed. And he can add more batteries. It all happens without re-entry of data. And that saved us so much money up front, but it also did something really magical. The whole spacecraft is in a mathematical model. So we can model behaviors, we can simulate what would happen if we did this maneuver, and we can troubleshoot the spacecraft. If there's a problem, once it's gone, once it's past Earth, if there's a problem, we can figure out what that problem is because we have the spacecraft completely modeled. The other thing we did in formulation is we created an augmented reality application that allows them to visualize the spacecraft earlier than they ever have before. So let's say you're telling a NASA person, headquarters person, okay, we're going to have a rover, it's going to be about this big. Well, isn't it better if they put on a HoloLens, like Marika is, and they see it standing in the room with them? And then they can shrink it down, pick it up, turn it around, look at it. They can make it big again, stick their head inside it, and look at how things are put together. And if you think about the implementation phase, even though we made this augmented reality app for the formulation phase, in the implementation phase, there's a guy whose job is to take this wire and plug it into that wire. And if you do it wrong, or you plug it into the wrong wire, guess what might happen? You short the entire spacecraft that's been built so far. You don't want to do that. Wouldn't it be great if you had an augmented reality model that you could just stick your head in, look at exactly how those wires are put together, and then do it and check it and make sure? So that's the sort of thing that we've done that helped build confidence, because as soon as we gave them that, they were like, oh, you know what else we could do? And that's like the most magic thing to hear. When you're trying to get UX adopted into an organization, and you've been fighting and fighting and fighting and trudging up that hill and pushing the rock, and you're like Sisyphus on the hill, and then all of a sudden they say, you know what else we could do? It's like, yes, we can. But we have 12 designers, and we have thousands of challenges at JPL. And there are 10 NASA centers, so that's tens of thousands of challenges NASA-wide. 12 designers are not going to solve tens of thousands of challenges in the timeline we need. So our solution to that was to workshop the hell out of it. We've had multiple events where it's 2 days of intensive talks, hands-on workshops. It's almost like a mini design conference, but instead of for designers, it's for everybody else at NASA. So all the system engineers, all of the project managers, all of the program officers who control the money can come to these and learn what we do. And not only are they learning about how to do it, they're learning why to do it. They're learning how to explain it to other people. We're deputizing them to be mini us's, which is amazing, because then they can take those skills. Like, we do storyboarding workshops where it's hands-on and we actually walk them through storyboarding their problem. They can then take that storyboard back to their project, and not only have they made progress, they've also learned a valuable new skill they can continue to use for the rest of the project. And then also, when they get in too deep, and it's too hard, or it's not what we taught in class, it's a challenge they just can't face on their own, they know exactly who to talk to. They talk to the 12 people who organized that conference for them. And when we join a project, it's a lot easier to explain that what we do is what we did at Systems and People last year. And they go, oh, yeah, design thinking, I know that. Yeah, let's start that. It's fantastic. The workshopping has been one of our best tools because it really has turned 50,000 NASA people into deputy designers. But then you got to make the thing. You got to make the spacecraft. We got to be involved in the Mars 2020 mission. This is a mission that launches in 2020. I know that's shocking. We're really good at naming, you guys. It's a twin of Curiosity. It looks just like her. There's some extra bells and whistles. She's got some features that Curiosity doesn't use, but she's a copy with stuff added. So Operations could theoretically be a copy, right? Except Curiosity, her operations model wasn't as good as they needed it to be for the budget of 2020. Let me tell you a little bit about rover operations. A rover drives this much in a day. She's going to go that far, and then she's going to like pull her arm out and do a little drilling or shoot a laser or take a picture. And that's it. That's 24 hours of activity for a rover. It's super, super slow, you guys, and it's because Curiosity's not that smart. If we tell her to go from here to there, and there's a big old rock right there, she's going to drive right through the rock. She doesn't know it's there. She's going to break her wheel. And guess what we don't have on Mars? Mechanics. There's nobody to change a tire. If she breaks, she's done. Mission over. No more science. So we have to be super, super careful. And we have to plan every motion. Like roll your wheels this percentage, and then turn to the left this many degrees, and then roll your wheels this percentage, yada, yada, yada. So it takes 10 hours to plan 1 day of activity on Mars. 10 hours. Mars 2020's budget was only 5 hours. We could only afford 5 hours. So they came to us and they said, hey guys, is there any way we can cut this process in half? And we were like, yeah, that's what we do. We can totally help you. And they were skeptical, to say the least. We came up with a bunch of ideas. We came up with all these plans. And they were like, meh, I don't think so. I don't know that that's going to work. So we organized some design sprints. How many of you guys have heard of the Google design sprints? Just a few hands. Okay. It's a 5-day process. You do something different every day with a cross-functional team that includes stakeholders, developers, designers, product owners, customers, right? At the end of this 5-day process, you have a product, a solution to a problem that you have tested. And there's usually a prototype. It's either paper or code. Doesn't matter what your prototype is. You have a prototype. You have tested it with some users. So it's a really amazing, intense sort of design workshop. And we had to modify it because most of us at JPL are on multiple projects. So it's really hard for us to say to our projects, oh, by the way, other project, you can't have me for 5 days. I'm not doing anything for you. So what we did was we did 2 weeks, half days. And it worked amazing. We had picked the 5 biggest problems. We were able to solve them all in 10-day chunks. 10 half-day chunks. 5 days? 5 man days? And then Mars 2020 was like, oh, maybe this can work. Maybe we can plan an entire day of rover operations in 5 hours. And we said, hey, wait, let's prove it for sure. So we brought 120 scientists to JPL for a 3-day role-playing activity where we simulated the operations of the mission as if it was already going on. And we found out not only, yes, we can totally plan a full day in 5 hours for sure with the real people who are actually going to do it. We also found a bunch of usability problems with our software that we had concepted. So yay, win, we found all these problems 3 years early. And we told you that your concept would work 3 years before any NASA mission has ever known that before. Huge win. And that win led us to Europa. Europa is the earliest that any UX designer has ever been involved in a NASA mission. With Europa, we're going to one of the moons of Jupiter. It's a super, super hostile environment. Major radiation. And we're doing this cool orbit where instead of just orbiting around Europa itself, the moon, and taking lots of pictures, our spacecraft would die in 20 days. We would like to have a longer mission than that. So we're doing this cool in and out orbit where we kind of dip into the radiation belts of Europa, take some pictures, do some measurements, do some stuff, and get the hell out. We process it, we think about it, we come back, we shed some radiation, we come back in, we do it again. So for that, we're able to go 2 years. But with those 2 years, all our money is front-loaded. The money's in building the spacecraft. We have a tiny operations budget. And so, guess what we do? Europa committed from day one to having a human-centered design process for their operations. That has never happened before, and it's directly on the successes of the Mars 2020 mission. They saw what we could do there, and they knew we could help them here. They knew that we could go where no UX person has ever gone before. And so we started with helping them tell their story. They needed to explain what was going on, why they had all these limitations, why the spacecraft had a CPU that's built in like the 1980s, because that's the most radiation-hardened thing, right? That's the thing that's going to live the longest, but it's kind of wimpy. So there are things we can't do that maybe fancier spacecraft can. But we're going to do more amazing things with it. We needed to be able to explain to the project scientists why we were automating all this stuff to help it be faster, how they could trust the automation. All of these things had to be explained, and so the first thing we did was we made a ton of storyboards. And it turns out they love storyboards. Storyboards get made into videos, and they get passed around, and they get shared, and they're also a great way to explore the things you don't know about. So, just a disclaimer, no, we're not going to see any tentacles on Europa, much as I wish we would. But we might possibly see like single-cell life forms. I don't know, maybe. And what happens if we do? We're making this plan super upfront so that we can have a tiny little operations crew, right? What do you do if you see something like this that changes everything? So we made a tentacle plan. We know we're not going to see tentacles, but it's fun, right? It makes you think. It gets people engaged. It's like the zombie training for survival people. It's the same concept in that it's a really fun thought experiment that helps you understand how you can do things if you run into those unknown unknowns. And the best way to do it when you have that tiny of a budget is to have practiced it beforehand. So of course, we're going to run design simulations. We're going to do all of the things that we did for Mars 2020, but we're doing them 2 years even earlier. The spacecraft hasn't been built yet. The spacecraft is still being designed, and we're thinking about what the operations will be. And think about that. All of the UX people in the world are like, man, if I could only get involved earlier. We are involved as early as it gets. We get to be there to help shape the architecture. And it's because we continually proved ourselves at every step of the way. We were willing to let the evidence and the data speak for us instead of just coming along and saying like, hey, we're UX, you should use us, we're awesome. No, we let the data speak and people listened. So it's after lunch. The too long didn't listen. Space is hard. Failure's not an option. We started small with software. The foot in the door approach, right? This is a tiny little investment, but we're going to help you save money. We proved return on investment, just like you would do in any company. We did that for NASA, where investment really is kind of a weird word. And every success we had opened new doors for us, and every door was bigger. And then the last thing we did that helped us get to where we are now, and goodness knows it's just the beginning of the journey, right? It's been 6 years, and JPL is 80 years old. So we've got like 74 more years to go before we're really all the way in there. But everything we did, we turned everyone we talked to into a design deputy and a design evangelist. Because by making them our partners, instead of just dictating what they should do, the immune system didn't react against us. We were adopted and we were embraced. So thank you very much for letting me talk about our process. Do I have time for any questions? I have time. Does anybody have any questions? Don't be shy. No questions, really? How about you?
Do you have any design system or framework that you use at the Human-Centered Design Group?
So the question was, do we have a design system or a framework that we use at the Human-Centered Design Group? And the answer is every problem has its own solution. They're all such unique problems. There's no one system or framework that we can apply. We tend to try a little bit of everything. So one of the last event that we had, the last 2-day workshop, was all about design thinking. And we used the Stanford D School's design thinking framework to try to teach people about how to solve problems in a way differently than they might normally. But as far as like, is there one that every designer uses for every project? No, they're just all too unique. Yes?
I guess that ties into the previous question, but you often have a lot of people who have their existing ways of approaching these engineering situations, and they have their own processes. And then when you come to a new type of mission project, from yourself at the human-centered lab, that you have to come in there and say, okay, we're going to do things differently this time. What's some suggestions on how you communicate to these people of how we're going to do it differently and how you can collaborate without seeming like a non-technical person coming in to change up the business process?
Yes, so the question was, how do you convince people to change how they're doing things without, breaking a bunch of china? The answer is you don't act like a bull. So I come in and I'm humble. I tell them, look, you've done a great job. You've been doing a great job for 80 years. I've talked to people who have literally been in their jobs for 40 years. It's the only job they've ever had. And they're the best in the world at it. And I acknowledge that. And I come in humbly. I am here not to tell you how to do your job, but to assist you in it. And that sort of approach really helps, because you're not telling somebody they're doing it wrong. You're not telling somebody they have to change. What you're telling them is that you're here to take away the boring parts, or you're here to make it easier, or you're here to let them do more of what they love. And that sort of approach is really, really great, because it instantly makes them want to help you, right? Oh, you're here to help me? Okay, I'll totally help you. It helps a lot. And the other thing is, I'm not afraid of being the dumbest person in the room, and in fact, I love it. This is the only job I've ever had where half the conversation is like, wrong. But it's amazing. And I can just own it. I can say, I am the dumbest person in this room. Help me understand why we're doing this. And assuming that the people who are going to be operating this spacecraft in 5 years are just like me, how can we help them understand? And it really opens a ton of doors and minds when you're willing to be the idiot. I'm really good at that. Yes? The question is the learning curve when you're designing for NASA. Yeah, so the follow-up was, is it difficult to wrap your head around the design problems? The answer is yes and no. The design space, aerospace, yeah, that's really hard to understand. It's almost like a crash course in aerospace engineering every day. I know more about orbital dynamics than I ever thought I would know. And I was a nerd growing up, so that's saying something, right? But on the other hand, there's a transaction going on. It's a lot like designing for e-commerce, in that you need to present the information to the user, allow them to act on it, and present a confirmation, right? The same principles of transparency, affordance, gestalt, all of the same principles you would use for any design problem are the same principles you would use to solve these problems. It's just the reason you're solving them is really confusing and hard. And a lot of the times I'll spend evenings reading technical papers, just trying to figure out what the heck that guy meant when he said that he needed to understand the delta velocity at this phase of the mission for every maneuver. Or I'll be looking up, we live in acronym hell, so I'll be looking up what the heck an acronym means and trying to figure out, okay, this acronym has 3 different definitions. I'm guessing it's this one. There's a lot of that. There's a lot of translation. And one of the people I work with actually said to me, I'm bilingual. I speak English and JPL. Any other questions? Right here.
You're launching a spacecraft that's meant to last 40 years potentially, the Voyager. Do you have technical limitations to deciding how you're going to, what platforms you're going to use? I saw the HoloLens picture
Yeah, so one of the question is, do we have technical limitations since our missions last so long? How do we know what's going to still be around 40 years from now? And the answer is that there are pieces of Fortran code people are terrified to touch because they don't know what it's going to do to Voyager. So you have to do a little bit of fortune telling, right? You, at some points, you're trying to figure out, okay, is this technology going to be here 20 years from now, 10 years from now, 5 years from now? And since it may not, how can we architect the system so that when something new comes along that's better, or when this programming language is end of life, or when this operating system is no longer supported, we can easily port to a new thing. And so that's part of the reason everything is so over-engineered, because we really spend a ton of time just trying to predict the future. And as we all know, predicting the future is impossible. So we're taking wags, wild guesses, and we're trying to figure out, okay, what will last? And then when we're wrong, we mitigate the risk there by being well architected. We build modular code. My designs are not cutting edge. I mean, you saw the stuff for the Deep Space Network. It's not the most beautiful, elegant stuff, but it's stuff that I think I'm not going to be afraid to show 20 years from now, because I'm not going to get to change it again, right? You get to do it once, and then those user interfaces are there for the rest of the mission or for the life of the network. And so you really just have to be conservative in all your guesses. Yes?
I'm wondering, why do you refer to spacecraft as female, and is that something adopted?
Generally in engineering, machines are female. And not all the spacecraft are referred to as female. I think there are a couple that people call male. I like to think that anything that is smart enough to leave the planet has got to be a girl. Just my bias. As a critical, so the question is, have I ever failed as a UX designer? Has there ever been a system too complex to make better? As a person who is very critical of myself, like every designer ever, yeah, I think everything I've ever done has been a failure. Absolutely. There have been systems that didn't get as usable as I wanted them to be. There have been systems where only an expert user could use it. The Deep Space Network is still that way. It used to take over a year of training, and with the new tools we're putting in place, we're going to reduce that to like 8 months. I'd really love it if anybody off the street could sit down and use those tools without reading a manual or going through a training class. I mean, that's the gold standard, right, of UX. That's why I'm here. But these systems are just so crazy. I mean, the signal levels and the need to understand the equipment behind the system is just so intense and deep that the best I could do so far is like a 25% improvement. Yes?
My question was relatively on the same line. So because the systems are so complicated, we can't try can my mother use this system to try and see whether it will make sense? Also because each department has its own context and specialty, is the same software moving through different teams? Do you tweak it so that it makes sense to a different user? Are there filters or facets to the same software?
So the question is, because it's so complex, you can't use the can my mom use it? And also, is there software that as it moves from department to department, you can tweak it so that different types of people can use it? It's a great question. The first thing is, yeah, because we can't do the can my mom use it, we use proxy users in JPL. So I'm testing with the DSN operators. I'm testing with people who have done operations on orbital missions before for Europa. I mean, that's the best you can do is proxies. Just because it's so complex that you cannot take it to Starbucks and have people look at it, right? It's just not going to make any sense. The other thing that we do a ton is there is a group called MGSS who is making multi-mission software. And so for the smaller missions that can't afford to write, $5 million worth of custom software to run their spacecraft, for the smaller missions that are more like CubeSats, cube satellites are like the size of a loaf of bread, and they're much simpler. For those, we're creating software that can be customized to the needs of your spacecraft. So you can pull back your telemetry, you can send commands, you can make connections, get health and safety data, you can get trajectory analysis, all of this, and it's slightly customizable. So you get the basic package, and then you can tweak it as much as you have the budget to do so. And if you don't have any budget to tweak it, it'll work well enough. And that's the sort of thing that we try to do as much as possible. There's a big initiative right now across NASA to understand the human capabilities that are out there and understand all of the human factors related people that we have, which is for the first time including UX. They're recognizing that UX really is all about human cognition. And so we're looking at ways that NASA centers can share stuff with each other, which also has not been historically done just because of the way budgets are. So I'm out of time. Thank you so much for your questions. I'd love to talk to you guys later.